What NASA has done as a result of this is they actually just recently, a couple of years ago, crashed a spacecraft deliberately into an asteroid with an attempt to change its orbit. So did it work? And in fact, it did work. It worked really well. They were able to change it, but you need time to be able to do this. And so, it takes less energy to move something if you have longer to do it. And so from my perspective, to quote an old friend of mine, 3 most important things when it comes to deflecting an asteroid are find them early, and find them early.
Hi, everybody. So we have a real treat today. We're going to hear from Dr. Amy Mainzer. She is a professor of planetary sciences at UCLA. She is one of the world's leading experts on asteroid detection and planetary defense. She protects us from all those dangerous things that could hit us. And she is the PI in something called NEOWISE, which, if my Wikipedia entry is correct, its purpose is to find, track, and characterize near-Earth objects. She received several exceptional scientific achievement awards from NASA. She's had an asteroid named after her. She is the host and advisor on a very popular children's show called Ready, Jet, Go. And she was the science advisor on one of our favorite films, Don't Look Up. So without further ado, please welcome Dr. Amy Mainzer.
Oh, thank you so much. It's really a great pleasure to be here just because, for many reasons, of course, I love talking about my favorite subject, asteroids and comets, and will happily talk about them anytime, anywhere. But most especially, I wanted to just talk a little bit about the importance of science fiction, film, and TV along several different axes that are important, to scientists like me. And so let's take a little tour through opportunity and risk from the asteroids and comets. So I'll take you back about a decade now, 12 years ago, and there was a kind of an unusual event that happened one day. And I was actually driving home from LAX when I was listening to the BBC and I heard there was an explosion over Russia. And I thought, well, that's weird, because we knew that there was going to be an asteroid passing on that day, getting very close. But we knew that that asteroid had no chance of hitting the Earth. So I thought, wait a minute, what's wrong? This can't be wrong. But it did hit. And I apologize if you speak Russian. I'm pretty sure it's going to be swearing. Lots of it here. Swearing. I asked one of my Russian-speaking friends, and he goes, yep, swearing. Yep. So. Swearing, pretty sure. Can't blame him. But in any event, people saw the contrail in the sky and they ran to the windows to look at it. But it was completely unexpected. And it scared a lot of people. And then, these poor guys, it was a powerful enough blast wave to literally blow the doors off of buildings. But there's a door on there, so they get out. They get out. They go out through the door. But, only one of them gets out through the door, though. But then these other guys come up, and it's like, hold on a sec here, wait. Okay, door closed. But there's still guys under there, so you should, anyhow. But yeah, so anyway, this was a complete surprise event. And about 1,600 people or so ended up going to the hospital because they all saw the contrail in the sky, and then they went to the windows to look, not remembering the whole thing of duck and cover. If you see a bright flash of light in the sky, you're not supposed to go to the windows, right? You're supposed to go away from the windows. And the reason this happened is because it was an explosion very high up in the atmosphere. And so it took time for the shock wave to propagate down to the surface of the Earth, and that's what happened. So that's why there was that long delay between seeing the contrail and the time that it took for the sound to arrive, the shock wave. So in any event, this was an asteroid about 20 meters across, which is sort of, I would say, roughly the size of this room. So it wasn't very big. That was it. But we'll talk about why it was able to do that. Something the size of this room is really not very big. So why was it able to do that? And how? So one of the questions that I've been interested in for quite a long time is just, okay, well, what about the next 100 years or so? Will there be a major asteroid or comet impact? And, again, it's not a problem that you should stay up at night worrying about. You really shouldn't. There's lots of problems like this. But, the question is, well, there's either going to be one or there's not. And so I have some ideas about this. But basically, okay, so if we really tried to break the problem down a little bit, it kind of boils down to two questions. So when and how bad? And the first question, the when part, okay, well, if we went and we looked carefully, if we searched the skies carefully enough, we could probably figure out where things are going and discover them and then predict where they're going to go. So in other words, we could answer the when part. But the how bad part is also the next question, because every day the Earth is constantly getting bombarded by tiny little pieces of material. So the when is happening all the time, it's just not very bad, because the little fragments are so small, it just doesn't matter. So the question is, when is something that's big enough to cause a big enough problem likely to hit? And so the question is the impact energy. Okay, so there's a couple slides I have in here that have a couple of equations, but I'll walk you through it. What we really care about is something called kinetic energy, the energy of motion. And this just boils down to the mass of the object, so how much stuff times the velocity squared. Okay, so you might think, wow, the velocity is pretty important to know because the energy is going to increase as velocity times the velocity. Well, we get the velocity, if we can find the object and measure its orbit, we get the velocity for free, right? We know that part. But what about the mass? Well, that boils down to how much stuff packed into a volume. So in other words, if you all remember back, volume of a sphere goes as the radius of the sphere to the third power cubed. So in other words, change the radius a very little bit and you get a really big difference in impact energy. So it seems to be important from this perspective to just measure the sizes of the asteroids in addition to their orbits. Okay, so two simple questions. I mean, there's other things that matter, of course. Things like, what is it made out of? The porosity. Does it have any little moons orbiting it? All kinds of things. Those things matter too, but less than just the simple parameter of just what's the size? How big is the asteroid? Is it a dust particle? Is it 20 meters? Or is it something larger? Okay, but let's take a detour. So those are my questions. So I wanted to just kind of take a quick detour back to, well, okay, why am I telling you all about this stuff? And how did I get here? And just highlight a little bit the role that science fiction played in all of this. Okay, so that's me at about age 9 with my first planetarium right there, that little yellow globy thing. That's my very first planetarium. But I was born in northeastern Ohio in a town that is noted for tire production. We had a river that caught fire back right before I was born, and we have a lot of shopping malls that are now dead. So we're really good at that. But I did not want to become a tire engineer. That just didn't sound appealing for some reason. And you might ask, well, why not? Why wouldn't you be excited about being a tire engineer? Because it is pretty cool. Well, unfortunately, there was this little movie that came out, and I'm told that I came out of the movie theater, and that was it. Also, some really good inspiration as a teacher is right about here at this part. So in my new job as a professor, I really take inspiration from, where is he? Oh, here he is. Yeah, this guy. I aim to instill fear in my students, just like Darth Vader did. So anyhow, yeah, that's, but in any event, yes. So Star Wars, that really had a profound impact. No pun intended. Basically, that was it. Somehow that movie inspired an idea that there was something else out there other than tires and dead malls, and it could be really exciting. And so, science fiction, I think, has an incredible role to play in not just communicating science, but it's also planting little seeds that go out there. And they're like homing beacons to some of us weirdos who see that stuff and really kind of think, oh, wait a minute, there's something else out there that's bigger and larger than my immediate environment. And I want to be connected to that. So I really appreciate the efforts that everybody puts into making good quality stories about science, because this is what draws a lot of us in. And for us, this was the thing that we had that made us want to do science in the first place. So in any event, so a little quick tour through the trajectory after that. So I left Ohio and came out west to a school in the north called Stanford, and then went on to Caltech, worked at a company, got a job, and worked on my first space mission. Because again, I just read every sci-fi book I could get my hands on, watched every show I could find, all the stuff I could find. Went on to graduate work, came south here at UCLA, worked on yet another instrument for another one. There was a graduation that happened in there somewhere. The first spacecraft, this one that's up over here in the right-hand corner, this one launched right after I graduated, so that's good. And then, and that helped me to get a job, actually, working for NASA. And after seeing it on PBS for all those years, I finally got to go work there, and that was really wonderful. So then got to work on the second space mission, and then finally that led to yet another launch, which was great. And then fortune took a turn for the hotter, and I went east to Arizona. But that lasted about 5 years. And then I got to come back and completed the cycle. And so now I'm back where I started at UCLA. So in any event, that's a little bit of how it all went. Okay, so in any event, I work on space telescopes of various sorts, but mostly lately, as Doran mentioned, I've been working on space telescopes that search for asteroids and comets. Because again, these questions were interesting. So back to our story. So the solar system, as I like to say, now is a very busy place. And you would think, because we know where galaxies are at the very edge of the universe, that means that we know where all the little asteroids and comets are in our solar system, the big ones and the little ones. No, we don't. So here's a little tour that I like to just kind of review because it just sort of sets the stage. So if we were sort of floating over our sun right here in the center, here's Earth, third rock from the sun, basically going around, right there it is. And we've got Mars and Jupiter way out here. And you can see there's this sort of band of green dots. So this is not actually an artist concept. This is real data. And you're seeing actual movement of real asteroids. This is what, of course, they're not green dots, sorry. But, you get the idea. This is real data, and this is their real motions on the sky. Right now, we know of about 1 million of these objects. And they stay in between Mars and Jupiter mostly, most of the time. Mostly. So they're stable on timescales that for astronomers are, reasonably long, like a few 100 million years to billions of years or so. They stay there. And that's great, but not entirely. Not entirely. Every now and again, something will happen. Basically, the gentle pressure of sunlight falling on the objects can subtly and slowly change their orbits a little bit. And then you'll notice a couple of things here. There's another effect going on. So I don't know if you can see this, but Jupiter is this little blue thing right here. It's very faint, but you'll notice there's kind of 2 bluish blobs of asteroids that move with Jupiter. So in other words, Jupiter's gravity is powerful enough to grab onto these asteroids and drag them around its orbit. So in other words, gravitational, we call these resonances. Jupiter's gravity can just grab onto it and pull something around with it. So you can get the sense that resonances, in other words, orbits that cross or interact with the other planets, can have a really powerful impact on an asteroid's orbit or a comet's orbit. And in fact, you can even see a kind of another example of a resonance here, these sort of 3 little ears sticking off of the asteroid belt. This is yet another kind of resonance with Jupiter. So again, Jupiter's resonances, its powerful gravity is sculpting the orbits of the asteroids. So you combine the gentle drifting pressure of sunlight with, every now and again, if you encounter one of these resonances, if you get too close to a planet, essentially, or you get too close to kind of one of the orbital frequencies that is in resonance with that planet, now all of a sudden it's like hitting a flipper on a pinball machine. Well, on astronomical timescales, okay? So, only 1 million years or a few million years, the orbit will change. But the point is, when it does, now it can do something different. Instead of just going around and around in this main asteroid belt band, now one of 3 things can happen to it. It can get kicked out. In other words, it can get pushed out to a further orbit. It can get pulled into the sun. And we actually see spectacular examples of this happening from our spacecraft right now. We can actually see the sun eating comets every now and again. It just fries them. Or the asteroid or the object can hit a planet. And sometimes the planet is Earth. So these red things in here are the ones that have leaked in from the main asteroid belt through a combination of these gentle kind of sunlight-influenced motions as well as resonances. And that's how they become near-Earth objects. And today we know of, maybe, let's say, 30 to 40,000 or so, about 40,000 of them now. I should update the chart. But basically, we don't know how many more are there. We have some ideas, and we'll talk about that. But, okay, a few misconceptions. Okay, so I do love The Empire Strikes Back. Obviously, it's one of my favorite movies. But there's some things that are wrong. No, does not look like this. So you know how the Millennium Falcon's cruising around and the space worms are trying to eat it, and so the Falcon is twisting through all the rocks trying to avoid the space worms. and the Empire and all that. Well, the thing is, our asteroid belt doesn't look like that. So in other words, if we were floating around near an asteroid, it would probably look more like this, just a bunch of dots. In other words, you wouldn't see large resolved floating chunks of rock floating that close to each other. The asteroids are really big, but space is even bigger, right? And so just the sheer volume of space is so huge that if you were floating around in the asteroid belt, you really would just see a bunch of dots. Okay, so in any event, another thing I like to kind of point out is, we see shooting stars if we have clear days here. And, the average size of these things is just a sand grain. That's how big they are. So most of them, if you see a very bright one, it might be the size of a grain of rice. And you think, well, how is it possible that a grain of rice can make a bright streak in the sky? And it's the same question about Chelyabinsk, the explosion over Russia. How is that able to make such a big explosion, even though it wasn't really much bigger than this room? Well, the answer is the typical speeds. Remember that energy of motion? The typical speeds are about 40,000 miles an hour. And so that's why. It's just moving so fast with respect to the Earth that the atmosphere is effectively a brick wall when the object hits. And it just is, all of its mass is turned into light and heat. And so that's basically what happens. So even the little rice grain becomes the equivalent of about 4 sticks of TNT when it hits the atmosphere. And that's why it's able to make that bright flash. So, okay, a little bit of terminology. And I kind of figured since we want to learn about how to communicate about hazardous asteroids and comets, I thought, well, the best way to do is just kind of give you a little dive into some of the jargon here, just very briefly. But basically, when we call something a near-Earth object, what we're really doing is we're just sort of picking a relatively arbitrary definition of things that get kind of close to the Earth's orbit. In other words, they get close enough that they're sort of within about 30% or so of the distance of the Earth to the Sun. So in other words, kind of one Earth-Sun distance plus an extra 30% on top. Why 30%? It seems like a pretty reasonable number. It's not super precise. Perihelion, that just means closest approach to the sun for the object. So in other words, just it gets relatively close within the volume around the Earth. Now we care about things that are both asteroids and comets. And what are these? Well, it used to be people kind of thought that these were very separate things, where asteroids were rocks and comets are mostly ice. But it turns out there's a much more complex picture now. They're kind of rocky mixtures with some ice and icy mixtures with some rocks and everything in between. You could think of it that way. But, we do know that they have a lot of variety among them. Just like rocks on Earth, there's a zillion different kinds of asteroids, and they range from everything that are, kind of crumbly gravel balls to really solid lumps of nickel and iron. So everything in between, lots of different kinds of rocks. And then our cometary bodies have all kinds of weird ices mixed into them. Water ice, carbon dioxide ice, ammonia ice, everything. So that's kind of, a little bit of the jargon there. But we do care about a particular set of the objects down here. And not all asteroids that are near-Earth objects are ones that have any real chance of hitting the Earth at all. There's a subset of them, about, say, 25% or so, that are the ones we pay particular attention to because their orbits now get very close to the Earth's orbit. And it doesn't mean that the object and the Earth would ever be at the same place at the same time. That's an impact. But in other words, the object's orbit just spends a lot of time close to the Earth's orbit. So they have something called a minimum orbit intersection distance, which is just a fancy way of saying how close do two circles get to each other, or two ellipses. That's all. And it has to be about 5% of the Earth-Sun distance. So in other words, when the orbit approaches to within sort of around 5% of our orbit, now we really pay attention to it because perturbations from the other planets and even the bigger asteroids can tug on the object, and over time they can change its orbit. And that makes it a little harder for us to predict where it will go over timescales of about 100 years. So those are the asteroids we're looking for. That's the ones we really care about. So anyway, okay, so how bad would such an impact be? Well, we just saw it really depends a lot on the impact energy. And that really boils down to how big is the object, first and foremost. Because the impact energy scales as that diameter of the object to the third power. So diameter times diameter times diameter. So small uncertainties in that diameter can result in big uncertainties in the impact energy. Okay, so I've got two examples here of two impacts, just to give you a sense of, how strongly the dependency on diameter really goes. And we have over here, this is Chelyabinsk, the one that exploded over Russia. And it made a hole about 6 meters across or so a meter, roughly a yard. So, made a decent-sized hole in a frozen lake. They managed to send divers down into this very cold lake and dragged up this largest piece of it right here. The object was stony, so it's kind of made of an ordinary stone. I've got a photo of it here in a minute that I'll show you. But basically, the upshot is, it broke a lot of windows, but fundamentally there was no crater, right? On the other hand, we got a real crater over here on the right-hand side, and this is called Meteor Crater in Arizona. And this is about a mile-wide hole in the ground, basically. And this crater was caused by something that instead of 17 to 20 meters across, is now about 50 meters, so a little more than double the size. But this object is made of iron instead of stone, so it's much more dense. So in other words, if you go from kind of 17 to 20 meters stony object and scale it up just a little bit and bump the density a little higher, and now instead of a kind of modest little hole in a lake, you get a giant hole in the ground. Okay, so that's a 50-meter object. So kind of now let's talk about, on average, how big are these things floating around out here? So I gave you 2 examples, but what about the rest of them? Okay, so this is our moon here, and for scale, I've got these 2. Now these are, I love these movies. These are not science fiction. These are real movies collected by a NASA spacecraft that a colleague of mine at UCLA flew, and they orbited the two of the largest bodies in the asteroid belt. So this first one here is called Ceres, and it has the distinction of being both an asteroid and what's called a dwarf planet. So I don't know if everybody remembers how poor Pluto got kicked out of being a planet. It's a dwarf planet now, just like Ceres. And I was actually at that meeting where it kicked out Pluto. It was really funny. I mean, I've never seen astronomers get so mad. It was really, really, really funny. I mean, people were just about ready to whack each other with their laptops. It was really something. They were very, very angry. Everybody was very frustrated about that whole thing. So, anyhow, will I say the definition is perfect? No, but I don't want to go through that again. So. Anyway, so this is Ceres here. It's round, and that's why it's part of why it's a dwarf planet. It's big enough that its gravity has crushed it into this round shape, just like our moon. But you can get a sense of scale. It's about 25% of the mass of the whole asteroid belt in just this one object. That's how big it is. And it's about the size of Texas, roughly. So Vesta, here's another one that's also pretty round, but you can see it's a little bit, not quite as perfectly round, but you get the idea. Okay, so in any event, those are some of the largest ones. That's the largest one right here, and then one of the kind of the top 2 or 3 below it. Okay, so if we now take a look at what I call the family portrait of most of the asteroids and comets, I would say the asteroids in this case, that we've actually visited with spacecraft. This is what it looks like for scale. Okay, so you saw Vesta over there relative to our moon. Well, here are all the other ones that we've actually sent a spacecraft to. Now, there's 1 million of these that we know about, and we've only been able to visit about a dozen or so. That's it. That's how hard it is to go into space. It's just really difficult. So, but you can get a sense of the scale. So you can see these ones down here just look like tiny, tiny little dots on the screen. Each one of these is roughly between a half mile and a mile across. Okay, so you can see our little 20-meter Chelyabinsk that broke windows and did not create a crater doesn't even show up on the screen. It's just much tinier, okay? So, okay, now let's take a look at what really big impacts have done to the Earth. On the larger side, we have one here that is called Chicxulub, and this is the one that took out the dinosaurs. This was a really, really, truly large impactor. This thing is thought to be somewhere in the neighborhood of maybe 5 to 10 kilometers across. There's some evidence it might have been a comet. And its impact energy was the equivalent of something like a factor of 10 times the whole world's nuclear arsenal just going off all at once. It was devastating. So the crater that it left was about 200 kilometers across, and we can actually see the rim of the crater right here in this radar image collected by a NASA spacecraft. So it was a big one. And what did it do? Well, basically, most of anything that was large died. Anything above about 50, 75 pounds, something like that, went extinct because the food web just collapsed immediately. And it really did have a profound impact. So you can see here, I've got a plot that I think is quite interesting, which is basically the diversity of life versus time. Going backwards in time about 500 million years or so, you can see extinction events happening. And what's going on here is this is how many different, what's called genera. So in other words, one level up from species. This represents how many different kinds of genera are there. So it's a diversity measure, basically. And you can see life's evolution is punctuated by these extinction events, the yellow triangles. And here's Chicxulub, right there. So basically, half of all the different genera are gone, and it comes back. Absolutely comes back in about, kind of 5 to 10 million years. It comes back. So, this whole climate change thing that we're doing, liberating lots of CO2 and pumping it into the atmosphere, well, we kind of already did the experiment here on planet Earth. So maybe, we don't want to do that again, because the planet will be fine in 5 to 10 million years. So just that's something to keep in mind. In any event, yeah, this is the KT boundary right here. So this is actually the boundary layer, or KPG boundary, where you can see big chunky fossils here and then just nothing. And then, stuff starts to come back after a while. So in any event, I think this is, kind of a fascinating parable for modern day climate change, because one of the big things that happened is all the debris got lofted into the air, it cut off the sun, but the other thing that we think might have happened is that the flaming debris rained down and lit most of the forests on the planet on fire. And what does that do? Well, that liberates a ton of carbon really fast and just pumps it into the atmosphere. So, okay, so like I said, experiment, the conclusion, it was bad. Okay, so how often does this really happen? Well, we know from counting asteroids and from looking at craters on the Earth and on the Moon, we can get some kind of a statistical sense for how often it happens. So we know that really big impacts like Chicxulub have to be rare because we're here, right? If they were truly common, we wouldn't be here. There wouldn't be time. Anything that would be complex would just keep getting wiped out before, I don't know, iPhones came along or whatever. But in any event, yeah, so we know that truly large impacts cannot be very often, but smaller ones definitely can. So who here played Asteroids, the video game, a lot? I call it research. That's my excuse. So it's actually a really good game because you hit the asteroid and it breaks apart into lots of small pieces, which then go and produce more small pieces. So it really is research. That's what I tell my mom when I sit there and just obsessively play asteroids to blow off steam. But in any event, there is definitely a larger number of small objects out there. Okay, so there are far more small fragments than there are of the really big objects. And that means that impacts from smaller objects occur with greater frequency. So we think, based on statistics, that the Chelyabinsk-size fireball impactors, something of order 100 years, something like that, maybe. But again, it's hard to predict random events on short time scales because our time scales are astronomical. So from my standpoint, the thing that I wanted to do was just say, okay, well, what about this 100 years? Not, the next 100,000 years, but this 100 years. So that kind of leads us to do a few things as a science community. And now in 1992, we actually got a pretty good idea that impacts can happen. So a comet was discovered that was going to have a close encounter with Jupiter. And it basically shredded the comet into little pieces, and then it actually hit the planet. And when it did, there was a pretty good discussion among scientists about what would happen. Would Jupiter just sort of swallow it up and nothing would happen, or would it do something detectable? So they were able to point the Hubble Space Telescope at it, and this is what they saw. Just for reference, this is the Great Red Spot on Jupiter, and that's about 2 or 3 times the size of the Earth. So there's the impacts. So each one about the size of the Earth. So yeah, so that kind of got people thinking. That plus invention of computers, thought maybe we should do something about this. Okay, so here we go. Here's Chelyabinsk on the opposite side of the size scale. The little thing that was pulled up, there was a piece. Okay, so this is actually my personal piece right here, a little bit that I have. And you can see it's a stone. It's one of the most common types of stony meteorites, and there's all kinds of little flecks of metal in it. You can see these little kind of lines running through it. That's from previous collisions with other asteroids that happened a long time ago. And the outside, of course, is burned black from passing through the Earth's atmosphere at that roughly 40,000 mile an hour speed. That's called a fusion crust. So in any event, all of this collectively has sort of said, well, maybe Congress at some point said to NASA, maybe you guys should do something about this. And so they gave NASA a goal in about 1998 to say, okay, you need to find 90% of all of the near-Earth asteroids bigger than a kilometer across. You know, that's big enough to wipe out most life on Earth. So go find all the, you know, or well, 90% at least of all the near-Earth asteroids bigger than a kilometer. And so it did actually take the community, about roughly 10 years to do that. And so we had found pretty good evidence by 2010, asteroids are. Now remember, notice I didn't say near-Earth objects. I didn't say objects, because objects includes comets. So we're just sort of leaving that there, okay? Just set that aside for the moment. 90% of near-Earth asteroids, though, but still, that was a big deal. So in any event, now we're working on trying to get down to a smaller size, about 140 meters. We'd like to find 90% of those objects. And you might ask the question, well, why 140? That's kind of a weird number. Well, okay, so you've seen what a 17 to 20 meter object can do. You saw what a 50 meter object can do. You saw what a 10 kilometer object can do, right? So somewhere in between there is, it can blow a hole in the ground to, it can wipe out life on the planet. So somewhere in the middle is probably a good place, you know, really try to get most of those. And this 140 meter number comes from analysis of basically trying to kind of balance what we think will be the risk from small near-Earth asteroids versus the comets that are still out there. So 140 meters, really bad day for, say, Southern California. So we want to find most of those. And we've been working on that now really hard. And so now we actually do have a Planetary Defense Coordination Office. And Adam McKay was really great on Don't Look Up to work this into the movie. And another, I think, wonderful example of how science fiction and film can actually, you know, really help communicate what's really happening in science. So this is a real thing now, and they keep track of all the asteroids with us. So here's the survey fleet. Unfortunately, this one, our first infrared space telescope, finally, after a very long, extended mission, it was supposed to last for 6 months, and we got almost 15 years out of it. It burned up in atmosphere in July. So it became a shooting star, which I think is fitting. But we're not done with this problem. So that's the thing. So this is what we found to date. And we're trying to kind of break it down by size here. I'm going to just hit the highlights, but the point is, this is the number of discovered asteroids as a function of time. And you can see that the curve is just going up and up and up. In other words, we haven't run out of things to discover yet. If we look at what we think are the really big ones, the 1 kilometer, you can see this red line here is kind of flat, which suggests that we got most of them. And our 140 meter mark is here, we think, and it's still going up. But you can see it's starting to flatten out a little bit. That's because our telescopes are limited right now in what they can see. The telescopes we're using at the moment, these are pretty small as telescopes goes. These are kind of about 1 to 2 meters across. They're not that big. So we've been trying to build, and then our space telescope went into the drink. So we really are trying to work on something new, which I'll tell you about here really fast. But basically, we think right now we know of sort of around maybe 40% or so of the 140 meter and larger objects, which leaves the vast majority of them undiscovered. And anything smaller than that, down to say 50 meters, it's a few percent. So we really don't know where most of the asteroids are. And that was a bit of a surprise to me, because I thought we just knew where they were. Turns out it's harder than that. So one of the fun things we did do along the way, we discovered this comet called Comet NEOWISE that got really nice and bright, and a lot of people were able to see it. But the thing about comets is they are different beasts a little bit. This one, we discovered it with our telescope. It was March 27th, and it made its closest approach to the sun. You can see it doing it here by July 5th. So in other words, comets come in with incredible velocities, much higher speeds than asteroids on average. So we tend not to have a lot of warning, which is why when Adam McKay asked for an object to be created for Don't Look Up, I thought, oh, well, this comet right here is a pretty good example. And I told him, I said, well, but you know, usually it takes like 5 years to build a spacecraft to go push an asteroid out of the way. Can't we show 5 years of design meetings? Oh, and monthly management reviews. Those are really great, too. So Adam said, no, you can't have that. You get 6 months. I said, all right, fine. Okay, 6 months. So, you know, we did have to compress the normal schedule for building a spacecraft from 5 years of monthly management reviews into 6 months. But I would have watched the monthly management reviews. I would have. There would have been 5 people who would have watched this movie. 5 whole people, mostly from JPL. But in any event, yeah, so this is a little clip. But it does sort of beg the question, what should we do if we find one? So in this movie, you know, they almost get it. They are almost able to successfully push the asteroid aside, but then things kind of go wrong.
And 27 are lost due to lateral control malfunction.
So they try to blow up the comet so they can steer fragments back to the Earth.
Simultaneous explosive separation stage now.
And it doesn't quite work. So they fragment it, but they're not able to stop the comet. So we would like to be able to do a little better than that in real life. And you know, the good news is there's actually some very good technical work that's been done lately. You know, the thing with this problem in Don't Look Up was, you know, they almost are able to push it aside in the first attempt, but then, you know, somebody kind of comes along and derails it, and they instead go with a much less well-tested and well-proven technology. So in other words, you can see what happens if you don't have enough time and you're not really prepared. You haven't actually demonstrated the technology first. So what NASA has done as a result of this is they actually just recently, a couple of years ago, crashed a spacecraft deliberately into an asteroid with an attempt to change its orbit. And so this is what they did. They actually picked an asteroid that has a moon, where the moon is almost that 140-meter mark. And it worked. It would have taken a lot of, I mean, if that thing were to hit, it would be a very bad day. But basically the idea is they were going to measure the change in the moon's orbital period around the primary asteroid and use that as a way to see whether or not they actually changed its orbit. So it's quite clever. Basically, they looked for the faint dimming of the light as the moon passes in front of the asteroid. And they're going to watch to see if it changes. So this is the result. Now, I'm compressing the first images here because it's a lot slower. But then in the last set, we'll step into real time. So there's the primary, and here's the secondary, the moon. And here, now these are the real time steps of imagery coming from it. You can see it's just a pile of shattered gravel. So did it work? This was a kind of a small refrigerator-sized asteroid hitting something 160 meters across, pretty big. So this is what they saw on the ground. And in fact, it did work. It worked really well. They were able to change it. Hubble Space Telescope got a great image. By the way, this is a natural object that experienced a collision, and here's what the dimorphous impact looked like. So it looks pretty similar. But point being, we did learn a lot. The asteroid, it was deflected. They did change its orbit, but you need time to be able to do this. And so, you know, it takes less energy to move something if you have longer to do it. And so from my perspective, to quote an old friend of mine, 3 most important things when it comes to deflecting an asteroid are find them early, and find them early. Because if you have time, you can actually explore your options, test your technology thoroughly, and don't have the don't look up scenario where you have to do something in a big rush at the end. And of course, we really hope after doing all kinds of surveying that we really find nothing that's headed our way. That would be the best case, and I would be very happy with that. So I'm not going to crank through all the math here, but if for those who are interested, I love that thing in the textbooks that says, the serious student will note that. I used to hate that. But in any event, yeah, the point being is that the amount of velocity change was about 3 millimeters per second. So if you crank the math, it takes decades with a fridge-sized asteroid to move something about 160 meters across. So the upshot is you do really need time to be able to do this. It works if you have enough time. Okay, so anyhow, I'm not going to step through all of this here, but basically, you know, there are other options. They are more dramatic. It depends on how big the object is, but all of them require the time that it takes to carefully build a spacecraft so that it will work, so that we don't have the don't look up scenario. Okay, so we have lots of different ways to approach this. I'm going to kind of flip through some of this, but we are using heat-sensitive technology to look for the asteroids, because if you have 2 objects, one with a very dark surface and one with a lighter colored surface, if we can search for them using the heat that they emit rather than the sunlight bouncing off the surface, we have a much better chance of spotting the object and measuring its true size. So that is why the telescope we're building, which is basically the successor to this one, which burned up in atmosphere in July after a long unsuccessful extended mission, we're working on a new one. Oh, and by the way, some of my favorite things, we got to stick a few little Easter eggs in Don't Look Up here. These images are the discovery images of comet NEOWISE. So it's what they look like. It's collections of little dots. In this case, the dot was fuzzy. That's how we knew it was a comet. And we were able to stick this little guy in here. This is one of our first near-Earth asteroid discoveries, so that was kind of fun. Adam was very patient. He let me get away with a few things like that. So in any event, this is the new one we're building now, which is sort of hopefully the bigger, badder cousin to our predecessor mission. And the idea is, it really is designed to go out and find as many asteroids as we can, and do so for 5 years. That's our goal. And hopefully we will get it built pretty soon. It's launching in, it's September 13th, 2027. So the spacecraft is in pieces right now, some of it in Colorado. A big chunk of it just left the Jet Propulsion Laboratory yesterday by truck to go off to Utah for more testing. We at UCLA are testing ground-based versions of the camera chips. We've already delivered the flight versions, so anyway, a lot of hardware being built right now. But the idea is we're going to be searching this region right here. So if you look down from the sun, you remember we've looked down before in that movie with the green objects. In this case, or you could say you're looking up because there's really no up or down in space, but take your pick. So let's say we're looking up under the solar system. A model of where we think the asteroids are looks like this. These are the ones we are looking for, the potentially hazardous asteroids, the ones with the very circular Earth-like orbits. So you can see they're scattered all around the Earth's orbit. And so what we want to be able to do with our new telescope, our old one could only see in this tiny little cone. It couldn't turn. But the new one, we have a big tall, basically piece of sheet metal on it that lets us point the telescope at the sun so we can, or near the sun, so we can block out the sun's light and see the asteroids on the other side of the Earth's orbit. So this is where we're going to be looking. We will complement the ground-based surveys, which tend to look opposite the sun at night. And we believe after we survey, hopefully for a nice long extended mission of 10 years, we think we will hit that 90% mark that Congress wants us to do that. So in any event, when the survey starts, we think it will look something like this, searching those cones constantly and discovering and detecting objects very quickly. This is only 1/15 of the true number of objects because, again, it's not an animation. It really is a simulation. So the computer got a little unhappy when I tried to add more. But in any event, that's what we think we're hoping to do here starting in late September. So to just kind of conclude about all of this, we do have a hard time as a species dealing with problems that are not, kind of right in our face right now. But we can solve problems that are long-term if we don't wait until the last minute. And I submit that this, like many other of these class of problems, is something we can do something about. So, is there going to be an impact in the next century? Well, hopefully, I think we're going to find out. And there's Comet NEOWISE peeking over the Hollywood sign, which I thought was cool. So, all right, folks. Well, with that. Thank you for the inspiration. And I can take any questions you have. But yes, thank you so much for the inspiration, by the way. It really is great. Okay, so does anybody have any quick questions or anything? I don't know what our time's like. Yeah, I see one hand back there. Oh gosh. Okay. Yeah, I know. This is like I'm traumatized from this, right? No. So the argument with Pluto was that they found another object that was bigger than Pluto, lurking out there, and then you got the problem of Ceres. You all saw it. That thing's round and it's really big. So why is that not a planet? And so when you add up all the number of things that we know about now that are round and that kind of are of that size category, it wound up being something like up to 200 things would have to be called planets. And then everybody got really mad about that because, we have a hard enough time teaching our students, 9, right? I mean, 200 is just ridiculous, nobody can do that. So in the end, the thought was, well, it really does represent sort of a different category of object. It's not the same, it doesn't form quite the same way. It's not quite the same evolutionary process for it as the regular planets. So yes, I did vote to kick it out, and I'd do it again. I would. It had it coming. Any other questions? Yeah. It just depends on the day. I try to think about it this way. This is why scientific notation got invented for this exact problem, because we just have to deal with so many big numbers or ridiculously small numbers, the scale of what happens inside the atom, too. So I guess I look at it like, well, I've been really lucky. I got to see some amazing stuff. What is it, the line from Blade Runner? The moon's off Orion. Wait, no, I'm getting it wrong, darn it. Okay, wait, no, I've seen starfighting in Orion or something like that. I got to see some cool stuff, okay? So it's been really wonderful to get to do this, and we're so lucky to get to do it. And it really takes, in my opinion, just like art, it takes a society that values knowledge and creativity. And so if we get to do these things, we do get to contemplate these really incredible things that are real, that are out there. And yeah, we're tiny, tiny, tiny little things. So small. Yeah.
Are you working on any film projects now that you could share with us?
Let's see. Well, I'm teaching a class right now, actually, Intro to Solar System, which is super fun. So I'm hoping I'll be doing some more education projects related to my mission, because we do need to produce some educational videos. So I'm hoping to do that. And I'm thinking about doing a podcast possibly about film and science, which might be fun. So I was thinking about that. Hoping to have that soon. Yeah.
How much do you charge for consulting?
Gosh, well, I do tell students, I said, look, you really need to be concerned with being the very best scientist you can be. That's the most important thing. Know your science. And then take some public speaking, and get comfortable talking to people about it. But the idea, in my opinion, I have always told them, the idea of trying to be a professional, in other words, making your living off of consulting is a whole different ballgame. I have always advised them, go to school, do your science, really, know your stuff, because if you don't, it shows through in anybody that you do work with. I guess I would say that more. In other words, point being, don't quit your day job. But the day job is the point for us, Yeah.
Do you believe in aliens? And if you do, when are we going to meet them?
Yeah, aliens. I love aliens. I tell my students, it's like, you can always answer aliens. I might laugh at you a little bit, but it's okay, No, actually, but in seriousness, there's some really wonderful things that have come about since when I started graduate school. When I was a grad student, we didn't really know about extrasolar planets outside our solar system. We suspected them. We could see forming star systems. We could see their dusty clouds, but we really couldn't see other planets. We didn't have solid evidence for them. And right around when I started graduate school, the first extrasolar planets were discovered. And now, thanks to a bunch of different telescopes and space telescopes, we now know about we know thousands of planets. And what's more, we know statistically that every star that you see in the sky has planets, most likely. And not just one or two, but probably quite a few. So that's real solid scientific evidence. So the question about aliens is, could life have evolved elsewhere? Well, for sure, we now know that planets are very common. And we didn't used to know that. And this isn't speculation, it's real data. So you can kind of figure the odds of, okay, well, if we now see planets everywhere, what are the odds that there's life everywhere along with it? So that's a harder question to answer. And right now, for us, with our technology that we have today, we can say a little bit about what those planets are like. We can start to scratch the surface. But that's been hard. And so right now, we don't have any solid evidence yet. But we at least know planets are common, and we're starting to know a little bit more about their nature. One more. Yeah. Oh, yeah.
While on your lookup, were there any clashes or things that you really had to fight for besides the management review meeting?
Yeah, he didn't like management review meetings. I don't know what's wrong with him. Everybody does. But, and scheduling meetings and budget discussions and risk management boards. I mean, those are also super fun. We had to compromise a little bit on the issue of the lighting inside the telescope in the beginning. The opening scene when she's looking through the Subaru telescope. Think of it this way. You have to turn the lights off, or you can't see anything, right? So in other words, it's really important that the inside of the dome be very, very dark. in order to not corrupt the measurements that you're trying to make. So of course, though, you know, I pointed this out to Adam, but then he very wisely said, "Yeah, but how are we supposed to film a movie in the dark?" You know. So we compromised on that one, and I saw his point. He's right. It would have been a much more boring scene, you know, just pitch black. Jennifer Lawrence is hard at work. It's pitch black. I mean, what are you going to do? So some of my colleagues complained about that, and I said, and then they were kind of like, all right, fine. So we compromised on that. In the back, yeah. Yeah, how can we, you know, what's the right approach? I mean, yeah, it's a tough question, I think, that in this case, you know, ignoring disasters is a bad idea, full stop. Right? It's not something we should do. And this is where I think artists can use whatever tools you have in your arsenal to communicate that. I have often thought that science tells us about the world. It tells us the facts. But art is what helps us to deal with the emotions we feel when we learn the facts. And sometimes the facts are bad news. So, in my opinion, that is why I like working with artists, because I think you have to use your wisdom as artists and your judgment to figure out how best to convey the message, because people should not do nothing. That's not the right answer. So you try different things and you see what works, I suspect. And I do love a good disaster movie. There's some really great disaster movies out there that are, you know, just fun and campy and cheesy to watch too. So in other words, I think humor is a powerful tool, because that helps us to look at ourselves with humility and be able to face the news, good or bad. So, one more question, yeah? Yeah. Yes, actually, so this is, there is a congressional law that says that NASA is obligated to go and find 90% of the near-Earth asteroids larger than 140 meters across. And they were supposed to have done so by 2020. So we're a little late here, but we're getting it done. Everything is always up for funding. As an aside, I actually will be going to Congress on Thursday for a hearing, so I will let you know how it goes on this topic. So yeah. I mean, well, like I said, I think, you know, civilized societies should have these things. So there's a lot of reasons for that, of course, but civilized societies should have a lot of things like this. We should be able to walk and chew gum at the same time. So anyway, that's my message to them. It's important. We should do it. So, and that's true of many things. But in any event, well, thank you all so much for your attention, and thank you. Thank you for inviting me.